Hi everyone, Lloyd Rieber here again with my next presentation of the course Statistics in Education for Mere Mortals. In this presentation I'll introduce you to the topic of descriptive statistics. Now we've already explored one of the main types of descriptive statistics, namely measures of central tendency such as the mean, median, and the mode. And of course you already knew a lot about that given your familiarity with averages. In this presentation we'll begin to explore the other main type of descriptive statistics, variability. We'll begin by exploring something called the standard deviation. Again, you'll need a solid understanding of these ideas in order to be ready for our next Excel spreadsheet example. Okay, let's get started.
Let's start with a very interesting example that comes from the sport of Major League Baseball. Ted Williams was the last Major League Baseball player to hit 400 in a season. He actually batted .406 in 1941. So that means that for every 10 times he was at bat, he got a hit 4 times out of 10, 4 actual at-bats, not counting walks and sacrifices and things like that. Now, an interesting question is simply, why is that? Why has no other Major League Baseball player since 1941 been able to break through the 400 mark? You might say that the players now aren't as good as they were back then. But you see there an interesting statistic that the overall Major League batting average has always been about 260, at least since about 1900. So the answer to this question, or I should say a theory as to an answer to this question, is one that we'll explore based on some of the ideas in this presentation. So before this presentation is over, we will come back to this question. We need to get a little more formal now in our use of language in statistics. In particular, we need to explore the two words population and sample. Both of these words, I think, have everyday meanings. Population, for example, people will usually think of a large group of people, like the population of a country or a city or a state. So you think of a large group like you see in the photographs near the top of the screen. However, a population is simply going to be defined by us. What are going to be the boundaries of a particular group? So, for example, maybe I would like to do some work with the Boy Scouts or the Girl Scouts. So if I am working with that troop of Girl Scouts that you see in the middle, and all I care about is their performance or how well they are improving in something I'm trying to teach them, that one troop can be the population. But if I would like to make some statements about Girl Scouts in the state of Georgia or the state of Pennsylvania and what I am doing to help the Girl Scouts, then I would be talking about the sample of Girl Scouts that I am working with. Now, this is not just semantics. One of the reasons why we have to make this distinction is because the statistics we are going to calculate may be different depending on whether or not we are going to be defining a group as a population or as a sample. Indeed, the word statistic really has two meanings. The first is that it simply describes something, whether that be a person, a group, whatever. The second meaning is that a statistic is an estimate of a population based on a sample of data that I happen to have. So this distinction between the two meanings is extremely important from here on out. So I have an important decision to make. I have a choice to make. Am I interested in collecting data on a population? If so, that means I have access to every single member of the population. That's not very likely in most situations. More likely is that I'm interested in knowing about a population, but I can only collect data on a sample. So I might be interested in helping an organization like the Girl Scouts, and I would like to be able to design something that helps all the Girl Scouts learn something, but there's no way that I can try that out and have every single Girl Scout go through this and collect data on every single Girl Scout. Instead, I would have to choose a sample and make some inferences. Or am I interested in collecting data on a sample but don't care about the population? I think this third situation is most typical in training situations, especially in business and industry. So while I might accept the fact that the population might be all of the employees of a particular company, what I'm most interested in, or what I'm only interested in, is helping a small group of employees to perform better in their job. I was hired to help this small group actually perform better in their job. So here's an illustration of what we've been talking about. We are interested in a population and we want to describe it in some way. If I have access to every single member of the population and can take a measurement, that measurement is called a parameter. Now, as I say, most of the time it's very impractical to have access to every member of the population. So we are going to use a process of sampling to take a sample, and that sample, of course, will be incomplete. It will not include the entire population. It'll probably include a very small number of members of the population. So again, we are going to describe that sample, and we describe that sample with a statistic. And so the statistic is used then to make an inference to the parameter. And I can't help but bring up a classic example of trying to describe a population, namely the United States Census. Every 10 years we try to count every single person who is living in the United States in order to determine how many representatives we will have in the U.S. House of Representatives, one part of the Congress. Now, it's kind of interesting because in 2000, for the 2000 census, there actually was an attempt to use statistical sampling instead of actually trying to count every single person. But that was ruled as being unconstitutional. And you can read an excerpt there. It is in the U.S. Constitution that we have to count every single person. So sampling was considered not allowed or not appropriate. This is obviously a very controversial topic, but many people, especially those who know something about statistics, really think this is a shame because it would save a lot of money, and they believe that the results would be essentially equivalent. Before we go any further, I want to talk a little bit about what I think is one of the most challenging aspects of statistics for a lot of people. And it's really just the fact that the mathematical symbols we're going to be using are going to be very strange and unfamiliar. So I don't think the concepts or the computations are very difficult at all, but how they are represented mathematically can be a big obstacle for people. And I just want to remind you that we have to get used to mathematical symbols. And for example, here are a bunch of mathematical symbols that I'm sure you already know and are very comfortable with. The plus sign, the equal sign, the divide sign, 3 ways to do multiplication with a symbol. And we accept these and we've grown accustomed to them. And we can see that they allow us to describe in very concise terms or symbols some very interesting and very complicated operations. And I just want to remind you as we get into some of these symbols in our next set of computations that the only mathematics that you will need is simple arithmetic. So don't let the symbols put you off, but you will have to take time to master them and to feel as comfortable with the symbols we're about to explore, just as you are familiar and comfortable with these symbols of basic arithmetic. All right, so here we go. We already know this statement, compute the mean for a set of numbers. We're very comfortable with that. Well, how do we express that in mathematical symbols in statistics? Well, there actually are going to be 2 ways depending if I am talking about a population or if I'm talking about a sample. So again, you look at these symbols and you're saying, what is this? But remember, it's simply the idea of compute the means for a set of numbers. So in the example of the population, we have a Greek symbol, mu. It kind of looks like in italics u, but it's really the Greek symbol mu. And that is equal to, well, we have another Greek symbol, which is the summation sign. So we're going to sum all of the scores, and that X, capital X, stands for a particular score. So we're going to sum or add up all of the scores and divide by, well, capital N is the total number of scores. So that's exactly what we've been doing. Now for a sample, we're going to show the difference of a sample versus a population by having it looks like to be almost exactly the same formula, except instead of the Greek symbol mu, we have something called x bar, which is again just the mean of the sample. So I would read that as x bar equals the sum of x, which is the sum of all the scores, divided by the total number of scores. The summation sign is actually the uppercase Greek letter sigma. Now the calculation we actually do is exactly the same, whether it be for a population or a sample. So in this case, it really is more of a symbolic difference between the two. The actual calculation is the same, but by using the symbols properly, I am able to understand if I am talking about a population or a sample. So again, the ideas are nothing that we haven't already explored. We're just expressing them now in the symbols of statistics. So there are two important types of descriptive statistics. The first are measures of central tendency, which we've already discussed and covered, the examples being the mean, the median, and the mode. But now we're going to discuss and consider measures of variability. So how variable or how varied the scores are. So here I've drawn two examples of the normal curve, one superimposed upon the other. They're both symmetrical, but you notice how one is wider or more spread out or fatter than the other one. There's actually a word that statisticians use for the shape of a normal curve like this, and it's called kurtosis. And that is not another form of bad breath. It's just a word that talks about or means the curve's quality of peakedness. But I like to think about it more in terms of the spread of the scores or the spread of the curve being wider or more narrow. So let's consider some ways to measure variability. So I'm going to lay out three methods. Method one would be to compute the difference between the highest and the lowest score. So if I gave a test and the highest score was a 90 and the lowest score was a 50, the difference would be 40. That's also called the range. And that sounds reasonable. You know, the highest and the lowest score, that gives me some sense of how varied the scores are. But, you know, note, it only takes into account 2 of the scores. So if I gave that test to 100 people, I'm not even considering the scores of the other 98 people. So what's method 2? Well, method 2 starts off by computing the difference between each score and the grand mean. Recall that the grand mean is simply the average of all of the scores. Well, great, and in fact, that's a very important statistic called a deviation score. So if I do that, maybe what I should do is take the average of them. Well, the problem is, and we'll look into this when we get into our Excel spreadsheet example, the answer is always 0. And you might be wondering now, why is it always 0? Well, if you think about what an average is, if the average was 75, for example, you're going to have a certain number of people who scored above the average and a certain number of people who scored below the average. So a person's score minus the average is either going to be a positive number or a negative number. So it kind of balances out, you might say, when you add up that entire set of deviation scores. So we need another method. And that method number 3, is actually going to be to compute this statistic called the standard deviation. So what we do is we square the different scores first, those deviation scores. Then we're going to take the square root of all of that. Now, when you square something, if it's a negative number, a negative times a negative equals a positive. So we're going to wind up with all positive numbers. And then, since we squared everything, we need to take the square root of it. So that's a pretty clever idea. As you will see in the formula, we will also be dividing by the number of scores. So in a way, it's more or less an average of how much each score varies from the group. So here's the formula for a standard deviation when describing a sample. which is not the same as trying to estimate a parameter of a population. And we'll talk about that again on the next slide. And here's this symbolism that we were talking about earlier, but it's exactly what I was describing to you a few minutes ago. So S is the standard deviation of a sample, and that's going to be equal to the square root of the sum of all those deviation scores squared. So I'm going to take each person's score, subtract from it the average or the mean of the group. Whatever that number is, positive or negative, I'm going to square it. So it's going to turn out to be a positive. I will sum all those up, and then I will divide that by the total number of scores in the data set. And then that value, I will take the square root of it, and that will be the standard deviation. And I'm sure this might be as clear as mud right now in your heads, but I assure you, when we take a look at it in Excel, it will seem very easy. It will seem, I would say, even simple. Okay, let's look at the formula again when we are looking at the standard deviation. This time, though, where we have a sample, but our intent is to estimate the population parameter, which would be trying to estimate what the standard deviation is for the population. So as you look at the formula, it looks almost identical. But what should jump out at you is, instead of dividing by n, we're dividing by n minus 1. You might also notice that instead of the capital S, we have a lowercase s with a little caret on top of it, which is actually would be called S hat. But it's simply trying to show you that what we're now trying to compute is an estimate. It's a standard deviation, which is an estimate of the standard deviation of the population. But why do we have n minus 1? Well, the answer is a little abstract, but let me give it a try. As you know, looking at the numerator, we have a person's score minus the group average. Now, the group average is the average from the sample. We don't know the mean of the population. And from statistics, the history of statistics, we have learned that that number tends to be a little too small. That is, it tends to underestimate the true value. So, since it's a little too small, we make up for it by dividing by a denominator that's also a little smaller. So when the denominator gets a little smaller, the overall value gets a little bit higher or larger. Now, also notice, of course, with a very small sample, let's say my sample was only 10, 10 minus 1 is 9, and that's a pretty big difference, dividing by 10 or 9. Now, as my sample gets very, very large, if I had a sample of 10,000, well, dividing by 10,000 as compared to 9,999 is not going to be as big a difference. So the larger the sample, the closer the estimate. Now, I'm sure that was not a very satisfactory explanation, and I'm sorry about that. This is one of those subtle points of statistics that you need to be aware of and to continue to study when to use n versus n minus 1 in the denominator. But the important point to be made here is the point we were trying to make earlier, and that is, okay, I have collected data on a sample. Is my interest only on that sample, or am I trying to estimate the population parameter? Now, that was much too abstract for my taste. So let's do an example, and I think you will find this will help tremendously in making sense out of all of that. So here's a little example that I like. It's, again, dealing with the Girl Scouts, and the Girl Scouts like to sell cookies, and it's a great fundraiser. Let's say there was a troop of 6 girls, and you can see I have a table here, and in the left column with the capital X at the top, right under boxes of cookies, I see what each girl in the troop sold. So girl 1 sold 28, girl 2 11, girl 3 10, and so on. And below that you see the sum of all those scores is 60. In the second column you see that we have the deviation scores, which is each score minus the average. So if I see what the average was, I take the sum of all those boxes of cookies, I get 60, and 60 divided by 6 is 10. So the deviation scores are going to be, again, those individual sales numbers minus the average of 10. So girl number 1, her deviation score is going to be 28 minus 10, which is 18. Girl 2, 11 minus 10 is 1. Girl 3, right on the average. 10 minus 10 is 0. Then you can see the next 3 girls, they sold boxes of cookies that were below the average, so they have negative numbers. So those are deviation scores, and at the bottom here I put in the other symbol for a deviation score. A deviation score, again, is the score minus the average, or x minus x bar. But another symbol for the deviation score is the lowercase x. And if I were to add those up, and you can do that, you will see that that sum comes to 0, and that's a good check of our work because mathematically it has to be 0. Now let's look at the third column, which consists of all the deviation scores squared. So as you can see, 18 squared is 324, 1 squared is 1, 0 squared is 0. But now you see the negative numbers, minus 5, is going to be squared, and the answer is going to be 25. Negative 6 is going to be 36, and negative 8 is 64. So all of the values in the third column are positive numbers. If I sum all those up, I get 450. So let's now compute the standard deviation. And in this particular case, I decided that we definitely have a sample, and I am not interested in estimating the population standard deviation. So I simply am going to be dividing by n. So you see down below in the blue box, I have the formula for calculating the standard deviation. So you can see I'm summing up all those deviation scores. I'm going to square those, divide by n, and then take the square root of that entire value. So you kind of move over to the next spot here, and it's just the same formula, but again I'm using the symbol x instead of x minus x bar, with the lowercase x being the deviation score symbol. So again, I'm going to square that and sum all those up, dividing by how many Girl Scouts I have, and then take the square root of all of that. So if I do that, you will see that I get a value of 450 divided by 6, and then you take the square root of that. So that would be the square root of 75, which equals 8.66. The standard deviation is 8.66. So the important question and concept that I have to wrestle with now is, well, what does that mean exactly, a standard deviation of 8.66? Well, first of all, if all the girls sold exactly the same number of boxes of cookies, if they all sold 10 boxes, for example, there would be no variation. There would be no deviation from the mean. And so the standard deviation in that case would be 0. Now, if the girls all sold a similar number of boxes, so that all of their averages were all hovering very, very closely around the group average, then you would have a very small standard deviation. But if you have some of the girls selling a lot of cookies and a lot of the girls selling very few cookies, then you have a very large variation, a large spread in that distribution of scores, and therefore you would have a large standard deviation. So here's our old friend, the normal curve. This time I've drawn it, as you can see, in a fairly colorful way. And honestly, I didn't draw this one. I found it doing a Google search of copyright-free images. This is actually a very interesting representation because along the bottom you see I have these little tick marks at very equal distance. They are equidistant. At the very center I have the mean. I'm using the population symbol mu to represent the mean. And of course it's a normal distribution, so the mean, median, and mode would be at that particular point. Now notice how we have these bands of blue again, that are going up like columns. And again, I want to point out that these are at equal marks along the axis. So what this really represents are standard deviation units. So one standard deviation to the right of the mean is the 1 sigma, and again, sigma is the symbol used to represent the standard deviation of a population. If I go to the left of mu, I have -1 sigma. And so again, those are equidistant, but notice that the column or the band of blue, if you can imagine that being filled with water, that's how I like to think of it, the amount of water that is contained to the right and to the left in that first band of dark blue is 34.1%. And that's a very important number. The next number in the slightly less dark blue is 13.6%. And then finally you see 2.1% in the lightest blue. And then at the tails you see 0.1%. Now these numbers are very important because they will tell you in standard deviation units how much or how many of the scores in a percentage will be found in that one unit of that one standard deviation unit. So if the normal distribution is very narrow, you're going to have those bands be closer together, but those bands are still going to contain that percentage of the scores. And you will see these numbers often in your statistical career, so these are actually numbers worth memorizing. Okay, let's end this presentation by coming back to the question that we started with. And this goes to the question of why have there not been any more 400 hitters since 1941 and Ted Williams? Well, the answer may involve the principle of variance. And this is a theory that was put forward by Stephen Jay Gould, the late paleontologist and biologist. And basically it goes like this, that he believed that the skill level of all players is more similar now than before. Or maybe stated another way, there is less variation between the best and worst players, including hitters and pitchers, of course. So someone like Ted Williams, who was an excellent hitter no matter what time frame in baseball we're talking about, Ted Williams was going to be facing, sure, some of the best pitchers of all time, but he was also going to be facing pitchers who were very much less skilled than we have today. So he perhaps had more opportunities to take advantage of the overall less skill level in terms of the variation of the pitchers that he was facing. So I don't know if this is a theory that I believe or not. It's again very controversial, but it's kind of a fun theory, and I love the way that it brings in the idea of variance to try to explain something, because again, the major league batting average has always been about 260. So I hope this presentation has at least set the stage for getting you to think about some important ideas, and I hope it is now going to have you be ready for our next Excel spreadsheet example. And as I say, actually doing the examples is much more concrete, and I believe once you do the example you will see very clearly how to do the computation. And because of the power of Excel, I do believe it's a very simple operation to follow. Yeah, there are many steps we're going to have to go through, but Excel is going to do the hard work for us. So, until next time.